session, and I'm pleased to introduce from the other Institute for Advanced Study, Matty Seiberg.
Thank you. David is always punctual, he shows up on time, and his talks never go over time. First, I'd like to thank the organizers, Ofer and Eliezer, for arranging this spectacular event and for inviting me to be here. I'm honored. I also like to thank David for having a birthday, which gives the reason to have this event. This is David. He's very happy. Later in the talk, we'll see why he's so happy. Normally, in events like that, and as I get older, I'm invited to more and more of them, the speakers enumerate the major scientific achievements of the birthday kid. And here I actually paid attention, and almost nobody said that. This is the highest form of praise. There is no need to enumerate all the achievements. So this is now a criterion for how successful one's career is. How few achievements are being mentioned in the... In addition... Only the H index. In addition to his many influential discoveries, David has also been a real leader. His impact on people's lives and careers, setting directions for scientific directions for institutions worldwide have been incredible, and we've heard a lot about it in the various talks, and all of us are very thankful to him. I think it's fair to say, whoops, what did I do? I think it's fair to say that David is the perfect physicist. He is interested in every branch of physics. He always asks questions. In fact, not only physics, it's all of science. He's interested in all of science, and perhaps even all branches of human knowledge. And he likes the unity of science. I think even other speakers have noticed that and mentioned it here. So I think it would be nice to give an interdisciplinary talk here, showing the unity of science. And I'll be talking about one of the current themes in condensed matter physics, but I'll present it from a high energy perspective, high energy theories perspective, and showing again that the synergy between the two fields and the relations between them. And this will be about a talk, about a paper that Ed Witten and I posted recently. And it talks about topological insulators. And this is our version of what topological insulators are. But I'm going to start with a lightning review of phases of matter and topological insulators for those people who don't know what they are. I'm sure everybody here is an expert, but let me review just to set the notation what we know about phases of theories. If we have a theory, what kind of phase can it have? The broadest classification is whether it's gapped or gapless. So gapless or massless, the correlation functions decay as a power at long distance. And gap means that they decay exponentially. So a low energy observer says that the operator is zero at low energies because all the exponents are set to zero. And in this case, we have power behavior. There is a further refinement. And the further refinement is here in the gapless case. There could be either a free theory, namely the critical exponents are simple, or there could be a more sophisticated non-trivial fixed point, and the critical exponents are more interesting. And in the gap case, the bulk theory could be trivial, or the bulk theory could be non-trivial. What does that mean? Here it's gapped, so there are no interesting local operators. All the local operators have exponential suppression in their correlation functions, and therefore we can set them to zero. But there could still be other observables. For example, there could be non-trivial line operators or surface operators. We can have non-trivial Bohm-Aharonov phases, Aharonov-Bohm phases between them. We can count the number of states in a compact space as an order parameter. And all these characterize the fact that there is a non-trivial topological field theory. So even though the theory is gapped, there could still be long-range order, which is topological in nature. So in this case, so that's in the gapped case, it could be trivial or non-trivial topological quantum field theory at long distance. But then there's even a further refinement. And the further refinement is that even if we have a gap theory, and even if there is no long-range topological order, so a person sitting inside the material would say the theory is absolutely trivial. There's nothing there. No interesting local operators, no interesting line operators. If we put the theory on compact space, there's only one ground state. So this is as trivial as it gets. There could still be something interesting if we have a boundary. So even if the theory in the bulk is completely trivial, there could still be something interesting on the boundary, and that's this further refinement. Either we have a trivial theory on the boundary, or there are massless boundary modes, for example, massless fermions on the boundary, or there could be a non-trivial topological quantum field theory on the boundary. So we have the classification first, what happens in the bulk, and then for a given bulk situation, there could be different things on the boundary. So in this case where the boundary is trivial, we say everything is trivial, but in these two cases, the bulk is trivial, the bulk observer cannot tell anything is going on, but there is still something non-trivial, and that comes under the name of symmetry-protected topological phases. So this is a very, very subtle characterization of the theory in the bulk. There's really nothing that the bulk observer could tell, and yet there's something non-trivial there that forces something along the boundary, and that's what we will talk about.
No, I can't resist saying as a particle physicist that this description of the phases of theory focuses only on the infinite range phenomena. Leaves a lot out.
Of course.
Like the real world.
Of course. Of course. No, there's more to physics than the extreme infrared. Like the theory of the strong interaction is not only pions, it's also deep inelastic scattering, to pick a random example.
Yeah, or ions, which are passive.
Exactly.
Or what they measure at LHC.
Yeah, that's not the whole story, but that's a start. That's a start. So let me continue with review of condensed matter physics, and apologize to the condensed matter physicist in the audience that might not be completely right. I'll talk a little bit about topological insulators, and first let me define what an insulator is. So an insulator, in our language, is a setup where we have a gapped and trivial bulk, and there is a unbroken global U1 symmetry, and I've denoted by big A. And big A is because big A is the gauge field for the electromagnetic field. This is the vector potential of the U1 gauge field. But I'm going to view it for the purpose of this talk as a classical background field. It's not dynamical, so I'm only using it as a device to diagnose the global symmetry. There's a global U1 symmetry, which will stay unbroken till I think the last slide of this talk. And that's what that's what an insulator is. It's a global U1 symmetry. It's unbroken. We couple it to a background field. The background field might have non-trivial topology. It might be very interesting, but that's what it is. And it's gapped. Now I'm going to assume that the system is also time reversal invariant. Somewhat carelessly, we high energy physicists call it parity. I'll use the term time reversal, which is a little bit cleaner here. And there might or might not be a trivial boundary. So the bulk is trivial. So what happens on the boundary? In an ordinary insulator, the boundary is trivial. But in the topological insulator, even though the bulk is trivial, the boundary could be non-trivial. And typically what we find is massless fermions on the bulk. So we have the bulk of this insulator, nothing there, and on the boundary there are massless charge fermions. But these fermions might also be lifted, and then we find a gap boundary state. So let's consider a simple example so that we know what we're talking about. So consider a theory with just free electrons, nothing else, and let their mass change. The mass is positive outside the material, m, and it's negative, minus m, inside the material. So we have kind of a step function. We can smooth it a little bit. So it's completely clear that in this case, this system has U1 symmetry and time reversal. That's manifest because m is real, and it changes from plus m and minus m. So everything is real and time reversal symmetric, and there's U1 symmetry. It's completely obvious. There's also charge conjugation, but that's irrelevant at this point. And as the mass varies from being positive outside to being negative inside, it has to go through zero, and therefore there are massless fermions on the interface. This was first found by Jacques and Rebbe. So on the interface, on the domain wall, we have massless fermions, and there has to be a massless fermion somewhere because m goes from positive to negative. Now, we can perform a chiral rotation inside the material. So we take this system and we just rotate the fermions by a phase. As we do that, the mass is positive everywhere, because we just did a rotation. But the non-trivial fact comes from the fact that we induce such a term because of the anomaly, an f wedge f term inside. And this f wedge f term can be thought of as a topological term, and it has precisely the value of theta equals pi with this normalization. So another way of describing this system is that we have classical electromagnetism with theta equals 0 outside and theta equals pi inside. And because of the interface, as theta varies from 0 to pi, the mass something has to be along the boundary, which are these massless fermions. So this is our system that we would like to understand better. The system of fermions, of theta being 0 outside and pi inside. The system is manifestly U1 invariant, manifestly time reversal invariant. So let's discuss that in a little bit more detail. So we get another perspective of that if we just start from the massless fermions. So we have a system in 2 + 1 dimensions with massless fermions, and this system is known. So first of all, it has a U1A symmetry, and it has time reversal symmetry. But there's an anomaly in this system known as the parity anomaly. So let's discuss it in a little bit more detail. The traditional way of saying it is the system has these two symmetries, but we cannot preserve both of them. We either preserve one of them, U1A, and violate T. This is the more standard way of dealing with it. Or we can preserve T and violate U1A. And this is common with anomalies. We have different requirements. We cannot satisfy all of them, so we have to sacrifice one of them. But there's another way out. And the other way out is to say that we are going to have both T and U1A. We're going to have both symmetries, but we'll sacrifice the 2 + 1 dimensionality. Something has to give, so what we'll sacrifice is this property, that the system is 2 + 1 dimensional.
You mean relativistic? It will not be relativistic?
No, it's relativistic. I take it relativistic. In condensed matter, it's not relativistic. But that's not what I'm talking about. I'm talking about adding another spatial dimension. It's not me, actually. It's this gentleman.
Yeah. So you don't break Lorentz.
I don't break Lorentz invariance in 3 dimensions. And so we preserve both U1A and time reversal. But the theory is no longer 2 + 1 dimensional. It needs the bulk. A first version of that came by Cullen and Harvey when they described the anomaly inflow. So we have an anomalous symmetry on the boundary. We have an anomaly from the bulk. It flows into the boundary. But the anomaly here is slightly more subtle than the anomaly that they considered. They considered an ordinary U1 anomaly, and here it's a discrete anomaly. It's a Z2 phenomenon of the same Cullen-Harvey anomaly inflow phenomenon. Now, it's really crucial that what we see here really follows from symmetries and anomalies. Now we can take the system, make it more complicated, then interactions. The conclusion is robust. The conclusion is robust in the sense that small perturbations cannot ruin this story. And we have massless fermions that remain massless. They cannot be lifted by small perturbations because of this whole intricate structure of symmetries and anomalies. So this is a summary of what I've been saying. Small perturbations are not going to lift it, but this immediately calls for the next questions. Can we add a large perturbation and gap the system? Can we take this system and change it while preserving the global U1 symmetry and time reversal and gap it? To what extent do we really need these massless fermions in the answer? Well, something will have to remain on the boundary because we have the anomaly. So can we replace the fermions by something else on the boundary that will suck the same anomaly that has to come in? Can we do that? And more concretely, can we find a topological quantum field theory that would saturate exactly the same anomaly? An example was given by these people. Now, I really want to highlight that this is a very hard question to answer. I do not know how to answer the question. Given that if somebody gives me a topological field theory in 2 + 1 dimensions, I do not know how to check whether it has time reversal symmetry, global U1 symmetry, and precisely the right anomaly to be coupled to the topological insulator. And this is particularly interesting for a subtlety that I did not mention here. Just as there's ordinary anomaly with F wedge F, there's also a gravitational anomaly, and there are even more subtle anomalies, and we do not know how to compute them in topological field theory. So the question is really, can we answer this question? Can we answer these questions without knowing how to compute in a given topological field theory this anomaly? There's some intrinsic property of this topological field theory, this anomaly, We don't know how to compute it, but can we bypass this question and still answer the question, the bigger question?
Why you don't like the massless fermions?
No, it's not that I love massless fermions. I love massless fermions. The question is there another option? No, I love that. Is there another option that will have the same?
Conceptually wrong with the fermions on their boundary.
No, the fermions are fine. We understand that. Research is about going into the place we don't understand. So we ask, is there something else that could be there that would give exactly the same anomaly? And normally when...
What are the examples?
I'm going to derive that example. Derive in a way that I think will make it obvious that what's right and what's wrong. So I'm going to extend the previous model in order to answer this question. So I'm going to extend the previous model, and the cast of characters will be an emergent gauge field, which I'll denote by little a, on the boundary. So I'm adding another gauge field living only on the boundary. And a scalar field W, which carries charge 1 under the symmetry, so it can Higgs the U1. So at first step, imagine this W has an expectation value. It removes the U1. I haven't done anything. And it's important that I haven't done anything because I would like to have the same system with the same anomalies. So I'm adding these two guys. And I'm also adding, so the fermion will be a fermion that is charged under these two symmetries, the global symmetry and the gauge symmetry. And I pick these charges 1 and 2s. And this 1, okay, let me explain that. If W has an expectation value, then this U1 little a is gone. I don't have to think about it. And this is the massless fermion we started with. Because it has charge 1, everything is the same. This number is even. Since it's even, it doesn't suffer from the parity anomaly. So this anomaly that I was talking about exists only for big A, but not for little a. So that's why this number has to be even, so I called it 2s. And I put parenthetically here that in the more advanced version of this talk, this s should also be even. But that's for more subtle topological reasons, which are actually quite interesting. So for the moment, is a parameter s, it's an integer, and we'll take it even to avoid difficulties. So as I said, I'm considering a quantum mechanical system that is not, which is supposed to be in the same universality class as the massless fermions. I'm going to address the question of, is there another topological field theory with the same anomaly as the original? Is there a topological field theory with the same anomaly as the massless fermion? So assume that somehow out of the mass of condensed matter physics, an emergent U1 occurs. This is not an outrageous assumption because they have it all the time. And there are also some quasi-particles like these chi and W. That's completely, yeah, that's common in the condensed. In our language, this is another model.
The necessity to create an actual model with built out of atoms and electrons for this.
Okay, so there are really three models. Model number 1, a Hamiltonian with atoms and electrons and some spins and interactions. This is really unpleasant, yeah. It's the real world, but it's annoying. Then there is the extreme infrared, which we would like to understand. I'm presenting here something which is neither these two. Something else that has the same symmetries and flows to the same infrared, but it has the advantage that I can analyze it. But as far as the question of anomalies and all that, I'll have a very, very concrete model that can be analyzed. And that's the goal of this exercise. So we should always keep in mind these three models. The mass at short distance that we don't know how to deal with, a toy model that has the correct infrared behavior. If we are lucky, it also has the correct quasi-particles, which will be crucial. I'll soon discuss them. The details of the masses of the quasi-particles and all that, we don't care about. We only care about what charges exist, what symmetries, what are the braiding statistics of the quasi-particles, and so forth. Okay, I can give you a whole lecture on that, about the proper normalization of Chern-Simons. I think we have an appendix on in the paper about that. And the proper way to think about it is actually not in terms of big A being a U1 gauge field, but in terms of a spin-C connection. If you want, I'd be happy to give you the answer. As far as this talk is concerned, U1 is an ordinary gauge field. The normalization of the properly normalized Chern-Simons is with 1 over 4 pi. That's the normalization for an ordinary Chern-Simon. Yeah, this is really a very interesting question that you allude to, but which I I don't think I can have enough time to discuss it here. So what do we see? We see a phase with W being non-zero. This guy is gone. There is a gap in the system. This is the system we started with. So that's a good system to analyze, except that we added some more stuff at short distance, and now we can try and see whether we can have a phase transition and lift all these guys. In order to do that, we add another scalar field to the mix, a scalar field that can give the chi's a mass. So we designed the charges here so that the chi can couple to phi and get a mass. So we just double the charges of chi. That's what we put here. So this is this phi. And now we go to another phase. W is 0, but phi is not 0. And as we do that, let's see what happens. First of all, time reversal was never broken. Everything is manifestly time reversal invariant. Also, the U1 asymmetry is not broken. To be precise, a linear combination of U1A, and this gauge symmetry remains unbroken. But the important thing is the gauge symmetry is spontaneously broken. But it's broken to a discrete subgroup. So the system is gapped. The fermions were lifted. No massless scalars, no massless fermions. We managed to achieve our goal. Just by adding a few degrees of freedom at short distance and moving in parameter space, we could find another phase of the same system, and therefore with the same symmetries and the same anomaly, such that the whole thing is gapped. And now what we have to do is to analyze very carefully what is left behind. Is there anything left behind to saturate, to compensate for the anomalies? I have two questions at the same time. Yes? I'll answer that. It's the same, there's a phase transition that I'm crossing. But the phase transition is such that A, I did not violate the U1 symmetry, time reversal, and the anomaly. And second thing, which is absolutely crucial, I can move very far in coupling constant as I go through this phase transition. But I keep H bar constantly small. This is maybe the main point of this talk. That's why I said at weak coupling in the introduction. Every single thing in this talk is done at weak coupling, and therefore there's really no room to hide, no fancy assumptions about something that happens at strong coupling. It's all should be done in front of our eyes.
So what you say that you've managed to give via the Higgs mechanism mass to this fermions.
Well, the Higgs is for the gauge field.
Gives the mass, then it's equivalent as we know to Chern-Simons.
Well, not quite. I'll answer this question in a lot of detail. That's the coming slides. Okay, how much more time can I get? I'll be happy to answer all questions. So the theory is weakly coupled, and it looks like everybody thinks we know what we should do, so let's just do it. We have a Lagrangian. Everything is weakly coupled physics. It should be straightforward, and it's almost completely straightforward. And we just analyze the massive spectrum. So first of all, we have W quanta. They are coupled. They are neutral under this global U1, and they transform under the unbroken discrete gauge symmetry. The key thing is that there is some unbroken gauge symmetry in the infrared, which started its life as being a continuous gauge symmetry of this emergent gauge field. There are also massive fermions, these chi quanta. They acquired the mass. They are neutral under electromagnetism, but they also transform under the gauge symmetry in a well-defined way. And there is also an interesting spectrum of vortices, because there is a U1 that was spontaneously broken to Z4S symmetry. So they are interesting vortices. And here we see the first interesting thing here, or maybe the second or third. We see an interesting thing. These vortices have a single fermion zero mode. So we just analyze things semi-classically. We ask, what are the zero modes? These vortices have a single fermion zero mode, and therefore they exhibit non-abelian statistics. So it's not just that we have this Z4S gauge symmetry. The infrared, the theory has massive particles, these vortices, and they have non-abelian statistics. So we see that something interesting has to happen here. So all the even vorticity guys have abelian statistics, and the non-abelian ones have the odd vorticity ones have non-abelian, and the even vorticity have abelian statistics. So now people say, oh, there should be a Chern-Simons description. So let's find it. Well, first of all, it's a discrete gauge symmetry. So you have to have a Chern-Simons description for a discrete gauge symmetry. There's a trick to do that which makes it relatively easy. That was found in a paper with Maldacen, Moore, and somebody else. We introduce another gauge field, U1 sub C, and we write a Chern-Simons term like that. The equation of motion of C says that this is a pure gauge, which just says that little a is a Z4H gauge field. And we can think of this new gauge field C as being the phase of phi that is eaten in the Higgs mechanism. So we had this complex field big phi. Its phase is the mode that is being eaten. We dualize it in 2 + 1 dimensions. We find another gauge field, which is this C. And the coupling of A here arises from the coupling of big phi to A that we had before. So now we integrate out the fermions. So we get a Chern-Simons term. And I put a warning sign here. This part is slightly imprecise, because when we integrate out the fermions with 1/8 pi that we get out front, we don't quite get a Chern-Simons term, but what we should get is the eta invariant. I don't know if Luis is here. Yeah. So you agree? And this was first done by Alvarez, Gomez, De La Pietra, and Moore in ancient history. So we have this term. So we derive this term because we have an unbroken discrete gauge symmetry, and we derive this term. And this is what we have so far. Yeah.
The theory is not topological, right? Because this gauge field coupled to metal field. So
Yes.
It's not topological.
That's correct.
Now when you integrate, you claim that you get just a topological.
Well, I'm just looking at what remains at long distance.
You get also an epsilon term by integrating.
There are tons of terms. There are tons of terms.
So how do
But
you know
there are tons of terms at short distance. A gap is formed. So the first thing I asked myself, are there any massless modes that remain? None. So what else can remain? A topological field theory. So now I'm not right. This is not the exact answer. This is only the exact answer in the long wavelength expansion. I'm going after the first term in the long wavelength expansion. So let's look at all the terms here and recognize them. This tells us that we have a discrete gauge symmetry. The term of little a with little a is this presentation of something that is known, the Darker-Witten term. There are various couplings of big A to little a, and there's a quadratic term in big A. All the terms here are properly normalized to be good Chern-Simons term, except the big A with big A, which has 1/8 pi. Everything else is even. So that's a sign that it reflects the right anomaly. So far it looks good. We have a topological field theory that we found at long distance, and it has the right anomaly. And this term should be interpreted as coming from the bulk of the system. And I really emphasize that this topological field theory is free. Everything is quadratic, so there shouldn't be any problem to analyze it. For example, the Wilson line of little a is exactly the quantum numbers to be this W quanta, the world line of this W quanta. So for every massive particle that I found before, there must be a line operator in this topological field theory. So far it looks good, but it's really important that this cannot be the whole story. There are several things that are wrong with this topological field theory. So what did I do? I just followed my nose. We got rid of all the massive modes. There are no massless modes. There's a discrete gauge theory. We described that. We integrated out the fermion. We found the correction term. And now I claim that this cannot be the whole story. It cannot be the whole story because there's a whole set of things that are wrong with it. First of all, we had the chi quasi-particle. This topological field theory doesn't have that. Second, this topological field theory is not T-invariant. We wanted something that is T-invariant. You can check the spins and statistics of these guys and charges. It's not T-invariant. And this is really an interesting problem. I emphasized before that there are vortices, and the vortices have non-abelian statistics. There are vortices here, the things that are really vortices of little a. This is a line integral. This is the Wilson line for this field C. They create precisely the right holonomy, or the precise holonomy of phi, of the gauge field that we do. But in this theory, these guys have abelian statistics. And when we worked out the massive spectrum, we saw that we should better have non-abelian statistics. And Luis is going to tell us that we were really careless when we used the Chern-Simons term. We had to use the eta invariant instead. So it's another sign that we're doing something wrong. So this cannot be the whole story. But all these problems can be simultaneously fixed. and we add to the system another sector that fixes all of them. So it turns out that there's a 3-dimensional, or 2 plus 1 dimensional topological field theory. For every topological quantum field theory, there's a corresponding rational conformal field theory that corresponds to it. And the simplest non-abelian one is the one associated with Ising. So this is the 2 plus 1 dimensional topological field theory, whose 1 plus 1 dimensional counterpart is the Ising sector with 3 line operators, the identity operator, and W psi, the line associated with the fermion that has spin 1/2, and W sigma, this is the line associated with the spin field with spin 1/16, and this guy has non-abelian statistics. So all we need to do is take this theory and couple it to what we had before, and then check that we got everything right. And this is the answer. We take the 2 sectors, we take a quotient of them by another Z2. This is getting a little bit technical. We write down all the line operators that this theory has. We compute the statistics and the braiding and the electric charges of every one of these lines, and they match what we found semi-classically. There's also a more detailed derivation that actually leads to precisely that. So the lines are labeled by an integer n, which is basically how it transforms under the discrete gauge symmetry, the vorticity v, which is the vorticity of this discrete gauge symmetry, and these are the particles, all the quanta that I discussed before, all the quasi-particles that I discussed before are all the quasi-particles that I discussed before are reproduced by this answer, and so this is the answer. So we started at weak coupling. I really emphasize we do every single thing with small h bar, and the analysis was somewhat subtle. We had these vortices with non-abelian statistics and eta invariant and this and that, but it's all basically semi-classical physics, maybe one loop, maybe subtleties of the fermion determinant, but no fancy non-perturbative dynamics that we don't have completely under control. And we showed that system has the 2 phases that we discussed. So let me come to the conclusions. First of all, yeah. You have to work out the spectrum. So if you just work out the spectrum of... From the action, we don't see it. It's not manifest in the action. There's actually a way of writing it that it's manifest in the action, but not the presentation I gave here. That's in the paper. But you see, it's highly non-trivial because, for example, this component here, W sigma, is spin 1/16. And the Z4S, if you work out the right, this works with odd V and with add S, so that puts a 16 in the denominator, which exactly cancels all the... It's actually quite miraculous that this thing manages to have the right symmetries. From this presentation, there's another presentation that makes it manifest, but it's less transparent for other reasons. Yeah, the action is not manifestly T invariant. It's T, if you wish, it's T invariant on shell, but not off shell. That's a way of saying it. But if you look at all the correlation functions, they are T invariant with the anomaly. So the partition function of this theory with any number of lines on every 4 manifold with a 3-dimensional, with a 2 plus 1 dimensional boundary, the correlation functions here are T invariant, namely that if you transform all the lines to the T conjugate, then you get the complex conjugate of the previous answer. So if there are no lines, all the correlation functions are real, for example. This is a non-trivial thing to check, that this thing is T invariant and the correlation functions are real. Or if you have braidings, you get the appropriate complex conjugation that you need for T invariant. This is the answer. So the first thing, yeah?
Yeah, so this is bothering me. So I have had some picture that I thought Kellen and Ari gave us many years ago that whenever you saw anomaly inflow onto a defect, it was telling you you were learning that there had to be some physical degrees of freedom on the defect that would actually carry the current. It seemed like a very nice physical picture, but now you're telling me you don't really need that.
Well, it doesn't have to be massless. In this case, the anomaly is a discrete anomaly, not continuous.
But the topological theory doesn't require that there's the massive modes are there. You can just completely decouple them, right?
No, but they still have to be there. They still have to be there. I can answer that in a different way. How much time do I have? Plenty of time. So I'll answer that. So let's go back to the beginning. We had theta equals pi inside, theta equals 0 outside. Why do we need anything on the boundary to begin with? Answer. Let's imagine there is a magnetic monopole in the world. Go to Cabrera's lab and we take that monopole. And we drag it into the material. So more mathematically, we take in a Tooth line and we bring it through the boundary. So we have a magnetic monopole which has electric charge 0 outside. Because theta is 0, that's what it is. We bring it inside. Suddenly it has electric charge 1/2. Where did the electric charge come from? Well, it had to come from the boundary. There must be charged excitations on the boundary that carry the mismatch in the electric charge. That's the argument, that there must be something on the boundary to compensate for the anomaly inflow. This is nothing but rephrasing Cullen and Harvey in this particular context. But the mass can be high. In this particular case, what happens is that if you take a monopole in, you take a monopole from outside and you drag it in, it has exactly, if you work out the quantum numbers, it's actually quite subtle, but the quantum numbers are deposited are precisely the quantum number of 1W quantum along the boundary. So there's a line operator for W, which can start at a point, and at that point, it's connected to a tooth line that comes from outside and pierces the material, pierces the boundary and goes inside. So, yeah. And I believe that if you have a continuous you have a continuous symmetry, and the anomaly is in a continuous symmetry, as in the original Cullen-Harvey paper, then there must be massless modes. Here it's more subtle because of this time reversal thing, so maybe you can get away with massive modes. But your question is actually very interesting. What if the masses of these massive modes is really infinite? Not very large, but infinite. That tells you that the mass has to be finite.
Yeah.
This is a very... yeah, it's not complete decoupling. These massive...
No matter how high they are, it's not decoupling.
Yep. No, it's subtle. That's why the system is so interesting. But it can be gapped. And you see, you can't argue, well, you can argue, but I presented the Lagrangian or a Hamiltonian. Everything is semi-classical. All the degrees of freedom are in front of your eyes, either elementary quanta in the Lagrangian or semi-classical things that you can see. I'm not pulling out of a hat another degree of freedom that maybe appears quantum mechanically and so forth. It's all very explicit. So in conclusion, I hope I convinced you that if you would still needed convincing before the talk, I hope I succeeded to show you that these are interesting things. They are interesting for condensed matter physics, but also interesting for high-energy physicists. These are very interesting quantum field theories that can be analyzed, and they exhibit rich phenomena. Some of them are phenomena that we high-energy physicists had encountered before, but there are also a whole set of new phenomena that exist there. And they combine ideas from mathematics, like this analysis of the anomalies, quantum field theory, which was quite interesting here, condensed matter physics, and I put some dots here, maybe even technology. Topological insulator might be good for technology. And if that's not unity of science, I don't know what is. And more specifically, we presented the weakly coupled theory. I basically told you what the Lagrangian is. There are some coupling constants and fields and charges, etc. That has both a global symmetry, U1 symmetry, and time reversal symmetry. And this system has two interesting phases. In one of them, we reproduced the original massless fermion, and therefore this system has precisely the anomaly to be the boundary of a topological insulator. And in the other phase, we found a topological field theory. So it was a gapped phase. In the topological field theory, it's the same Lagrangian, has these two phases. And I emphasize that this was very, very explicit and calculable. So there's no room to hide. Everything can be done. Even though it's weakly coupled, I mentioned some of the subtleties, and they're actually, it's full of subtleties, even though it's weakly coupled. But these subtleties that we have no excuse. We really have to figure out because it's all weakly coupled. And as a course of doing that, I did not present it here, we found new consistency conditions on quantum field theories that describe condensed matter physics. New consistency conditions that were sort of spelled out before, but sort of mentioned before, but now we really spell them out carefully. And not only that, we showed that sometimes these consistency conditions have anomalies. The Lagrangian seems to satisfy the consistency condition, but it doesn't. So that's a new thing, and if I have more time, I'll be happy to explain that. We also found many more models. That's easy to do. You just take what we had, throw in a few more gauge fields, a few more fermions, a few more scalars, change the parameters, this condenses, that condenses, and so forth. And there's a rich spectrum of possibilities. We also generalized this point of view, to the study of what is known topological superconductor, where the U1 asymmetry is really replaced by Z2. That's all that matters is the Z2. And now we can run the whole story. In this case, it has all sorts of new interesting subtleties that we discuss. But I really emphasize that we did not come close to closing the subject. There are many, many things that can be done, many interesting questions that should be addressed. And there's only one more question I had to answer, which is, why was David so happy in the first slide? And that's why he was happy. Oh, that's very interesting. So far I ignore that, but they have to be discussed. And I can write other models with fermion, with this charge and that charge and so forth. They have exactly this anomaly that we need, but do not have the right gravitational anomaly. So one of them is kind of an R-wedge R. So when we start with the fermion with the step function in the mass, and we just do a chiral rotation inside, we induce F wedge F, but we also induce an R wedge R. So that's an anomaly that has to be there. But there are other anomalies that could be there and they're not, and you have to make sure that your topological field theory does not have that anomaly. And then there is the more subtle anomaly that I mentioned in the new consistency conditions that I did not even discuss here. But that's yet another level of complexity.
I have a very nice question, actually. I don't understand why we are insisting on Lorentz invariance in connection.
We don't. We don't. There's no need to insist. This system,
You can regularize and break Lorentz.
yeah, this system that was discussed here has Lorentz invariance that doesn't have to be there. And it also has charge conjugation symmetry that doesn't have to be there. We answered the question of finding the gap space by imposing more constraints on ourselves. This is the same answer that Gary gave. Now, we answered, now you can ask, can we do better with Lagrangians, with systems that are not Lorentz invariant? And maybe we can do better than that. This actually is a much general question. We always think that when we gap the system, and so the system is gapped, there's a topological field theory in the infrared, and so forth. We've heard that many times, but I don't understand why it has to be topological. I don't understand why. It turns out that it's always topological. It's always Lorentz invariant when it's gapped. I don't know why. We managed to get...
Topological maybe is just because we are looking on minimal, the simplest one, right? As we use topological. The Lorentz line is unclear for me from this measure. This kind of...
Well, we put ourselves in a tighter box, and we found the answer. You can take and break Lorentz invariant. The answer we got is robust, right? Take this system and add some small Lorentz violation. It's not going to change anything I said. Now, whether there are other possibilities that are not connected to this, which are Lorentz violating, maybe. I assume the answer is yes, but I don't know how to prove it.
Just take what is the difference between in condensed matter many models have the first derivative. Time derivative is of the first order. And Lorentz invariant time derivative is of the second order. And it depends on the bulk theory. You can change your bulk theory to having time derivative of the first order. Nothing really changes. Well, there are some subtleties because upon quantization, the first derivative time derivative of the first order is a little tricky, but not really too tricky, and it's known what to do. So that's sort of, I will think it will come out automatically.
Was this a question?
No, I just, it's an answer to
Ah.
some sort.
Zohar? Yeah. Sorry? Yeah. Can you speak up because some people in the audience talk at the same time? Ah, excellent. Excellent question. No, it is because this is an excellent question, so I'll answer that. I'm glad you asked that. The Lagrangian that I wrote actually has another U1 symmetry whose current is star F, and the operator that violates it is a monopole operator as opposed to the vortices. That's right. There is a charge operator under that symmetry that is neutral under all the gauge symmetries, but it violates the global symmetry. So what we have in mind is adding it with a small coefficient to the Lagrangian. That breaks the global symmetry. This is very common, but I emphasize that this can be done at weak coupling. Because the coefficient in front of it is small, it does not affect the dynamics. It's exactly as in the Polyakov model, we add it to the Lagrangian. But this is actually a very interesting object because this subtlety that I mentioned, that I said that I did not explain, is that this guy sometimes is a fermion. When it is a fermion, I cannot add it to the Lagrangian. So that's why there's another subtlety. I said that S has to be even. If S is odd, the guy that you mentioned that we really need to add to the Lagrangian in order to break the symmetry is a fermion. But that's just the tip of the iceberg of a very rich story that is associated with this operator.
Okay.